Hello everybody, welcome to 8.3 Trigonometric Identities. Today we're going to learn to define odd and even identities and then rewrite trig expressions, and then we're going to apply angle, sum, and difference formulas to find exact answers. Alright, so first let's talk about even versus odd trig functions. So a couple things to remember. We talked about even and odd functions earlier in the year, where we would plug in, we would find negative or f of negative x and see what kind of result we could get and determine if the function was either even, odd, or neither. If you don't remember that, I believe we did it either unit 2 or unit 3. It was somewhere, it's been a while. So just as a refresher, even functions are always going to be symmetric about the y-axis, and odd functions are going to be symmetric about the origin. And what this means is essentially, if we take f of negative x, and we can rearrange the formula, and it produces what was just f of x originally, that's what's known as an even function. And if we can take f of negative x and produce negative f of x, then we have what's known as an odd function, right? So I'm just gonna plug a couple things into Desmos here. So here we have sine of negative x. You'll notice that it looks a lot like sine of x, but instead of going up initially here, we're gonna actually go down. So what we're gonna do is, remember, this is sine of negative x, and what I'm gonna show you is I'm gonna prove to you here that sine is actually an odd function. And the way I'm gonna do that is, well, if I have sine of negative x, and I know that sine is odd, then I know that this will be the same as negative sine of x. So now you'll notice that we have a red graph here. When I click negative sine of x, it just turns blue, because the negative sine of x graph overrides the sine of negative x graph, proving that sine of negative x is the same as negative sine of x, meaning sine is odd. All right, so let's do the same thing for cosine. If I have cosine of negative x, right, in order for this to be an even function, I would have to say that cosine of negative x is the same as cosine of x, right? Well, watch what happens when I click cosine of x. Boom, same function. So sine is odd, cosine is even, and then if you want to take a second to think about what this would make tan, right? So if we have tan of negative x, we have this. You'll notice it's the same thing, but the little squiggles are kind of going the opposite way, if you want to call it that. Well, now we're going to show that tan of negative x equals negative tan of x, like that, which means it's what? If you said odd, you're correct, right? So sine and tangent are odd, cosine is even. This is going to be important because if we have sine of negative x, cosine negative x, tan of negative x, and we want to turn those into trigonometric properties that we can use, or trigonometric functions that we can use, which we'll be talking about trigonometric identities here in the next little section, we can't really do much with it if we have this negative x, if we have the negative sign connected to the x value, right? But if we can put the x out in front, or if we can get rid of the negative sign altogether, that's going to actually help us solve these problems. So basically, just a quick refresher, sine and tangent are both odd, cosine is even. All right, so let's go ahead and look at a few of these identities. And what's cool is I'm going to teach you some tricks first, and then we're going to go over a pretty basic problem. But essentially what you're just going to have to do with these is you're just going to have to do a bunch of these and kind of figure out what the kind of patterns you can get are. But essentially what we're going to do in these kinds of problems is we're going to use these trig identities here to help us kind of almost like a geometric proof. We're going to work both sides of the equation down until we get the same thing. Now, sometimes it'll just say simplify this side, and you'll want to break it down as much as possible and make it as few amount of terms as possible. But essentially the idea is that we want to be able to transform these so that we can manipulate them in ways that we'd like. So just look at a couple of these here. We have tangent equals sine over cosine. We talked about that when we first started doing the unit circle in the last unit. We have the Pythagorean identity, which you'll be able to diagnose that you can use it pretty quickly based on the fact that we have some second degree sine and cosines here. And then we also have a 1. So if you get a number, or if you get sine or cosine, both being squared, that's usually a good sign that you might be able to use the Pythagorean identity in your problem. Cofunction identities are going to be pretty straightforward. These are the only ones that are going to have pi's involved, right? And you'll notice that essentially what this is saying is that if I take sine and I shift it over pi over 2, I'm going to get cosine, right? Same thing. If I have cosine and I shift it over pi over 2, I'm going to get sine. Then if I take tangent and shift it, I'm going to get cotangent, right? This is basically saying that sine and cosine are very similar because you can kind of just shift them to get the other one. And then this is saying that tangent and cotangent are kind of similar in the way that sine and cosine are similar. So yeah, if you see a pi, you're probably going to be looking into these cofunction identities. And sometimes you can even use the conjugate to kind of flip these things around, and there's a bunch of stuff you can do with these. So, all right, and then last we have our odd even identities, which are the ones we just learned, right? Sine of negative x is sine of x, or negative sine of x, and then cosine of negative x is cosine of x, and then tangent, also being an odd function, is tangent of negative x equals negative tangent of x. All right, so just to give you a couple hints, because I know we haven't jumped into a problem yet, right? Our problem is going to be, we want to prove that tangent of negative x times cosine of x equals negative sine of x. We want to prove that this side of the equation equals this side of the equation, and we're just going to try to simplify this left side to make it look like the right side here, okay? Now, here's some tricks you can use in these kinds of problems, because there's going to be a ton of different problems. The best way of looking at this is, what does your problem look like? And it's kind of obvious sometimes which ones of these you're going to use, especially when you apply some of the tricks I'm about to tell you. But like, if you see a pi, you know you're going to be using this. If you see second degree functions or numbers, you might be using Pythagorean identity, right? If you see negative x's, you're going to have to rewrite that so that there's no negative x's, and that'll help you solve some stuff. So, all right, so let's talk about these tricks. So the first thing you're going to want to do is rewrite everything in terms of sine x and cosine of x. Now what this means is if you have sine of negative x or cosine of negative x or anything with a negative x, you're going to want to change those to where there's no negative near the x. All right, so odd and even identities, you're going to want to take care of those initially. The other thing you're going to want to do is tangent, cotangent, cosecant, and secant can all be written in terms of sine and cosine, right? Tangent is going to be sine over cosine, cotangent is going to be cosine over sine, cosecant is 1 over sine, and then secant is 1 over cosine, right? So we can rewrite all of those in terms of sine and cosine, and now we can just kind of worry about two things that we have to deal with instead of a whole bunch of them. All right, the second one's just going to be factor when possible, and then the third one is use conjugates to use the Pythagorean identity. There's going to be some conjugates you can use, like for instance, if this is sine squared x plus cosine squared x equals 1, you know, you can also think of this as like 1 minus cosine squared x equals sine squared x. And like I said, you can play around with those a little bit. If you do problems with those, you'll be able to pick up on it pretty easily. So let's just go ahead and do the problem that they gave us here. So we're going to prove that tangent of negative x cosine of x equals negative sine of x. So what's the first step that we do? What's the first trick? The first trick is always to rewrite everything in terms of sine and cosine, right? So the first thing I notice is I have tan of negative x, cosine of x, right? So the cosine of x is fine. The negative sine of x is fine. It's this tangent of negative x that we're going to have to do a couple things to get it in terms of sine and cosine. So the first thing I'm going to do is, okay, well, I notice that this is tangent of negative x. And I also know that tangent is an odd function, right? So I know that tangent of negative x equals negative tangent of x. So I'm going to take the negative, and I'm just going to kind of put it out front. And I'm going to get negative tangent of x cosine of x equals negative sine x. Well, I know that tangent of x is the same as sine over cosine, right? So if I have negative sine of x over cosine of x, right, because that would give us negative. So negative sine of x over cosine of x times cosine of x equals negative sine of x, right? All we did was take this negative tangent and turn it into sine over cosine, right? And then you'll notice that, well, we can actually, if we want to, we could take this cosine of x, and if this helps you out, I would recommend doing this. You can actually take this cosine and think of this as cosine of x over 1, right? Well, this is a fraction. If we multiply fractions, we can eliminate things that are on the top and the bottom. So we can actually cancel out both of these cosines of x, and we're going to be left with negative sine of x equals negative sine of x, which proves that the left-hand side does indeed equal the right-hand side. So first, like I said, all we did is we rewrote tangent using the odd function rule. Then now that we know that this is negative tan of x, we can write this as negative sine over cosine, and then we cancel out our cosines, and that's it. And that was a pretty simple one, but we got to use our odd even identities, and we got to use our quotient identity, so we got to use a couple of them, right? And there's going to be tons of different problems. We could spend 3 hours going over all the different kinds of problems you could see with these, but a lot of the times it's going to be just rewriting things and kind of just going through problems to be able to see the different patterns that you see. Okay, so that's it for when it comes to the trigonometric identities. the last thing we're going to learn today is angle, sum, and difference. Now, you'll notice that I'm going to show you this question, and then you're going to look at it and you're going to go, oh, wait, can't I solve that problem in 2 seconds? And technically no, and I'll explain why, okay? So the question's asking, what is the exact value of sine of 75 degrees? Now I know what you're thinking, okay? Boom, sine 75, and we're already in degree mode, so we don't have to do anything about it. There you go, boom. 0.96592588263. That sounds really exact, doesn't it? Well, it's actually not, right? This is an irrational number, or we can assume it's an irrational number because it's like, 15 decimal places here. So that's not exact, right? There is an exact value for this, and we can find it. And we can find it using our sum formulas and our difference formulas. All right, so the way to look at this is, in order to find sine of 75, we need to break up 75 degrees into pieces that we actually know. And if we think on a unit circle, there's a bunch of different degrees that we know, right? So if we just kind of quickly draw a unit circle over here, right? And we're mostly just worried about this first quadrant, right? Because we could figure out the rest. But we know 30 degrees, right? We know 45 degrees. We know 60 degrees. You might use 90. It's possible, right? But these are going to be the main ones we focus on, right? And what we're going to do is we're going to add or subtract any combination of these numbers because we know the exact values at these numbers, right? So if we're trying to find sine of 75, we can use sine of 45 plus sine of 30. And now we're going to use our sine sum formula because we're using sine and we're using the sum of 30 and 45. And you'll notice that all these formulas are different. There's not really a need to memorize these formulas, right? You just need to know when to apply the one that you need. So in this case, like I said, we're using sine, we're using 30 plus 45, so we're using sine and we're using addition. So our sine of 30, right? If we look at our formula, we have sine of alpha plus beta equals sine of alpha times cosine of beta plus cosine alpha sine of beta. And what this is saying is alpha is just going to reference our first number, which we're going to choose as 30, and beta is going to reference our second number. So this is sine of 30 cosine of 45 plus cosine of 30 sine of 45, right? We're just kind of plugging these things in. All right, so let's use our sine sum formula. We have sine of alpha plus beta equals sine alpha times cosine beta plus cosine alpha times sine beta. And what we're going to do is we're just going to plug in what we have. So we know that we're going to refer to this as sine of 30 plus 45, right? So 30 plus 45, 30 is going to be our alpha, 45 is going to be our beta. So let's plug in our stuff. So we have sine of 30, cosine of 45, plus cosine of 30, sine of 45. And you should recognize all of these terms here, right? Sine of 30 is 1/2. Cosine of 30, square root of 3 over 2, right? Cosine of 45, square root of 2 over 2. Sine of 45, square root of 2 over 2. So you see how now we can use our reference angles that we have before, right? Or we can use our unit circle as a reference, I should say, so that we can find these literal exact values, right? So now we get, okay, sine of 30 times cosine of 45. So 1/2 times the square root of 2 over 2 plus cosine of 30, square root of 3 over 2, times sine of 45, which is the square root of 2 over 2. And this is exact, right? So now we just need to simplify. So we have 1/2 times the square root of 2 over 2. We just multiply across, right? 1 times the square root of 2 is the square root of 2. And then 2 times 2 is 4. And that's going to be plus square root of 3 times the square root of 2, which is the square root of 6, over 2 times 2 is 4. So we have the square root of 2 over 4 plus the square root of 6 over 4. And if you remember your radical addition properties here, you might as well think of the square root of 2 as an x and the square root of 6 as a y. You can't add them together. They're completely different numbers, but you can combine them so that way we can get this all into one term, so that we could rewrite this as the square root of 2 plus the square root of 6 all over 4. And this is an exact answer, right? So real quick, just to show you, let's do this real quick just for fun. Square root of 2 plus square root of 6 over 4. So we have square root of 2 plus, oh, I don't want to contain that all in there. Square root of 2, let's just evaluate that. Okay, so answer plus the square root of 4, okay, right? Or no, it was the square root of 6, shoot. let's minus the square root of 4. There we go. So plus the square root of 6. Right, so 3.83. And then all that divided by 4. We get 0.9659, right? Which is literally the answer that we got before if we scroll up a bunch. There we go. Same answer. 6959. There's going to be a little bit of rounding, right? But that's kind of the idea, right? We have the exact same answer, but this answer here is the actual exact answer. There's no rounding. There's no irrational number. I mean, these are irrational, but there's no, this is exact, right? We're not doing any rounding whatsoever. So basically, to answer the question, when would we use these formulas versus when would we just use our calculator? This word right here, the word exact. If we're looking for the exact value, we need to come up with something like this. And the only way we can do that is by using these formulas so that we can get the actual absolute perfect unrounded numbers here. All right, excellent. So 8-3, we learned to identify even and odd identities, even being cosine, odd being sine and tangent. And then we rewrote trig expressions, right? I gave you some hints on how to solve things, and we took you through kind of a more basic one, but we got to see some of those things in action. And then I showed you the sum and distance formulas, or sum and difference formulas, and then showed you how to use the sine sum formula for one of these here to find the exact values of certain numbers that we can add together. So, all right, so that is it for 8-3. I will see you in 8-4 next time.